Let's think back way back to the beginning of this year. And we did limits. Remember when we did limits way back at the beginning of this year?
Yes.
Yeah, good. All right, that's a good answer. So we did those limits, and the first thing we always did with a limit was we
Plugged in x.
Yeah, plugged in the x value that was given to us. That was always the first thing that we did. And if we got a number out, that was good news, right? Yeah. But sometimes we got out something that looked like 0 over 0, right? Sometimes we got out 0 over 0. And what do we call that?
Indeterminate.
Indeterminate. All right. It's like you guys vaguely remember some stuff. That's good news. So we got these indeterminate limits. And when we had the indeterminate limits, we had a bunch of different ways that we were able to deal with them, right? For example, we would factor. That was one of the things that we did. We multiplied by the conjugate. Sometimes we did like a U substitution. Occasionally we would use like the sandwich theorem to like prove some limit for it. Or we had to use limit properties. We did all kinds of different things. Remember doing all kinds of different things? Yeah. Yeah, I remember doing all those things.
All the things.
Yeah, and it was just a giant pain, and you didn't enjoy doing it, right? But you did it because you had to, right? Does that sound about right? It would have been nicer if there was like an easier way to go about it. True?
Yes.
Yeah. Well, now there's an easier way. Okay. That easier way is called L'Hopital's rule. Okay. Sometimes it's spelled with an S in there, so it looks like Hospital's rule, and you might see me spell it that way too, just so you're aware. So L'Hopital's rule says that if you have a limit that is indeterminate, so it's in the form 0 over 0, rather than try to factor or do one of those other methods, you can take the derivative of the numerator of that fraction and take the derivative of the denominator of that fraction and just reevaluate the limit of that new quotient. So I can find the derivative of f at a, and I can find the derivative of g at a and evaluate this, and this will be the exact same thing as what the actual limit to the original function is. Okay? Does that make sense? So all you have to do is take the derivative, and plug in your value. So let's look at one. It's pretty easy. The limit as x approaches, I don't know, how about 3 of x squared minus 3x over x squared minus 7x plus 12. We're going to do this two different ways. One, when we plug it in, what do we get? We get 0 over 0, right? True?
Yes.
So using L'Hopital's rule, and very irritating, they want you to write out on the AP test when you use L'Hopital's rule so that they know what you're doing. Okay. So you're going to write, using L'Hopital's rule, this limit should be the same as the limit as x approaches 3 of the derivative of the numerator, which is
so we keep them separated. We don't do product rule or
we
quotient
definitely
rule.
don't do product rule. But yeah, we also definitely do not do quotient rule. It's just the derivative of the numerator divided by the derivative of the denominator. It is not the quotient rule because we're not actually taking the derivative of this function. It just works out. And there's a fairly, it's not too complicated of a proof, kind of like a working backwards proof that we can prove that this is equal to this. I'm not going to do the proof. If you want to look it up, you can. But it's not actually taking the derivative of the entire function. It's taking the derivative of the top and the derivative of the bottom. Okay. So it just becomes 2x minus 3 over 2x minus 7. And if I plug in 3 to that, what do I get? 6 minus 3 over 6 minus 7 should just get -3. Easy enough?
Yeah.
Cool. And just to illustrate that I'm not crazy and just making up a bunch of garbage, if I'd wanted to find this limit by factoring, I would have taken an x out of the numerator and factored the denominator into x minus 3x plus 4. Not x plus 4, x minus 4, because I got a factor. Canceled the x minus 3's and got the limit as x approaches 3 of x over x minus 4, which would be 3 over -1, which would be still -3. Good or no? Great. This only works if you have an indeterminate limit, 0 over 0, and there's going to be another form that we're going to talk about also. But for now, only if you end up with 0 over 0. If you plug in the numbers and get, 7/3 to your original function, and the answer is just 7/3. Don't try to take the derivative. Don't just look at it and say, oh, it's a rational function. I should be able to use Hopital's rule. Plug in the number, make sure you get 0 over 0. Then you can use it. Good or no?
Good.
All right. Let's do a couple more. Since these are limits, the first thing that we should do before we even bother to use Hopital's rule is we should plug in the 2 and make sure that this is 0 over 0. So if I plug in 2, what do we get?
Zero over 0.
Oh, wonderful. All right. So this should be then the same as the limit as x approaches 2 of of
2x over 1.
2x over 1, which should just be 2 times, that's not a 2, 2 times 2 over 1, or just 4. Good or no?
Good.
Great. What about this other one? What happens when I plug in 0?
It's 0 over 0.
0 over 0. And then so using L'Hopital's rule, and I'm just going to abbreviate this each time with putting an L dot H dot above the equal sign. But I have been told by the College Board that this is not good enough. You have to actually write out L'Hopital's rule using L'Hopital's rule. So you need to write out using L'Hopital's rule every time that you use it, even though that's kind of stupid. You have to do that. So using L'Hopital's rule, we'll take the derivative of the numerator. What's the derivative of the square root of 1 plus x? Should be, that's root u, right? So 1 over 2 root u times the derivative of 1 plus x, which is just 1. And then the derivative of -1 is 0. So we'll just ignore that. And then all over 1. And now we'll plug in 0 to get 1 over 2 times the square root of 1, or just 1/2. Good or no?
Good.
And probably a whole lot easier than trying to multiply this by the conjugate and then having to factor and then having to cancel, and that's a huge pain. And nobody wants to do that. As long as you can easily take your derivative using the chain rule there, should be easy enough. Okay. So what do you think would happen if when I plug in my, I do my L'Hopital's rule, and suppose I plugged in 0 here and it'd come out to be 0 over 0 again?
Could you find the second derivative?
Yep, we could just do it again, right? Take the derivative of the top and the derivative of the bottom again and plug it in. And what do you think would happen if that was still 0 over 0?
Or derivative?
You just keep doing it as many times as you need to until you get to something that is no longer 0 over 0. So if we end up getting another indeterminate, so if this indeterminate, or this is indeterminate, just use the rule again. And you can do it as many times as you need to, as long as you continue getting 0 over 0. As soon as you don't get 0 over 0, if you get 0 over 7, then your answer is 0. If you get 7 over 0, your answer doesn't exist. If you get 7 over 5, your answer is 7 over 5. So you can use L'Hopital's rule again as many times as needed. So let's take a look at one where we'll have to do that. The square root of 1 plus x minus 1 minus x over 2 over x squared. That one doesn't look like it'd be very fun for multiplying by the conjugate, does it?
No.
No. First off, what should we do? Plug in 0? Square root of 1 is 1, minus 1 is 0, minus 0 is 0, over 0 squared is 0. So we got 0 over 0. So we will, using L'Hopital's rule, now we will look for the limit as x approaches 0. And what's the derivative of root 1 plus x?
1 over 2 root 1 plus x.
1 over 2 root 1 plus x. And then the derivative of minus 1 is 0, and the derivative of minus x over 2 is minus what?
Two.
No. Minus x over 2, that's the same as minus a half x, right? What's the derivative of minus 1 half x?
Negative 1/2.
Negative 1/2, all over 2x. Now we plug in our 0, and we've got a half minus a half over 0. We got 0 over 0. So we'll have to use L'Hopital's rule again. What's the denominator going to be this time? The 2x's derivative is going to be 2, right? And the minus 1/2 is going to be 0, so we won't have to put that. We just need to find the derivative of this. This thing right here is 1/2 of 1 plus x to the negative 1/2. So what will that become? Its derivative ought to be the derivative of 1/2 of 1 plus x to the negative 1/2.
Negative 1/4 times 1 plus x to the negative 3/2.
Great. Times the derivative of 1 plus x, which is just 1. So don't have to put that. All right, now we plug in our 0, and we end up with negative 1/4 of 1 to the negative 3/2 divided by 2. 1 to any power is just 1, right? So we have negative 1/4 divided by 2, which ought to be negative 1/8. Any questions on that? Everybody good with that? No questions? Everyone's good? All right. Remember this one? You guys remember doing this one?
Yes.
Remember how we did this one? We had to like set it up as a sandwich theorem problem using like a circle with a triangle and then a sector of the circle and then another triangle, and we had to make this big inequality. Then we had to use the sandwich theorem with the inequality to show that this equaled what? To show that this limit equals what? This is one you were supposed to memorize. What does this limit equal?
1.
it equals 1, right? We know this equals 1. But if we just plug in the 0, right, it's 0 over 0. Well, now that we have this nice, easy L'Hopital's rule, we don't have to go through and do all of that sandwich theorem stuff. Derivative of sine is cosine. Derivative of x is 1. This is now just cosine of 0, which is 1. And I'd argue that that is significantly easier than what we did using the sandwich theorem. Would you agree?
Yes.
Yes.
Yeah, isn't that great? Yeah, so now when you forget that the limit as x approaches 0, sine x over x is 1, you'll just use L'Hopital's rule and then you'll remember it. Good or no?
Good.
Good.
All right, let's do a different indeterminate form, infinity over infinity. So this is, I don't think we talked about this one, but infinity over infinity is also indeterminate. And so if we have this form, we can also use L'Hopital's rule. And so first off, let's see why this is infinity over infinity. If we're looking at the secant of pi over 2, right, as we approach pi over 2, that's like approaching 1 over the cosine of pi over 2. And what's the cosine of pi over 2?
0.
0. So this is like 1 over something very close to 0, so a very, very small positive number. And what's 1 divided by something very, very small? It's getting very, very close to 0. One divided by a tiny little decimal becomes a very large number, doesn't it? Yes, it does. And then we on the bottom have 1 plus, what is that, sine x over cosine x? I guess I could write pi over 2 in here. And the sine of pi over 2 is 1, and the cosine of pi over 2 is still very close to 0. So this is 1 plus 1 over basically 0, which is also 1 plus infinity, or just infinity. So everybody agree that that would be infinity over infinity? Because remember, we're not getting to pi over 2. We're not making this undefined. It's just approaching a vertical asymptote when secant and tangent hit pi over 2. Good or no?
Good.
All right. So since it's infinity over infinity, we can use L'Hopital's rule to find the limit. This should become the limit as x approaches pi over 2. What's the derivative of secant x?
Secant tangent.
X, tan X.
Secant x tangent x. And then what's the derivative of 1?
0.
0. And what's the derivative of tangent?
Secant squared.
Secant squared. All right. Well, we can at least cancel out a secant, right? So this just becomes tangent x over secant x. Well, as x goes towards pi over 2, tangent of pi over 2 is infinity. And secant of pi over 2 is also infinity, isn't it? So what would I need to do?
Do it again.
Derivative.
All right, we could do it again. So using L'Hopital's rule, this is going to be the limit as x approaches pi over 2 of, well, the derivative of tangent is secant squared over secant tangent, which is just, I don't know, something's up with my pen right now. There we go. Cancel out the secants again. Now it's just secant x over tangent x, which is infinity over infinity, isn't it? Well, if we did it again, derivative of secant is secant tangent, and the derivative of tangent is secant squared. We're going to just go right back up to this, right? Which will then just bring us right back down to this, which will bring us right back up to this. We're just going to get in this infinite loop of getting this same indeterminate form. So maybe we need to do something else with it at this point. Right, because otherwise it's just turning into an infinite loop, isn't it? You guys see that that was going to just cycle around and around and around?
Yeah.
Okay. So how can I rewrite tangent x over secant x?
Sine over cosine over 1 over cosine.
Sine over cosine over 1 over cosine, which ought to give us just
Fine.
sine x. And what's the limit as x approaches pi over 2 of sine x?
One.
1. Spectacular. So sometimes you might end up, especially with trig functions, in this annoying little loop that's sort of difficult to deal with. And so we have to find a way to simplify the trig functions in order to find the limit. Good or no?
Good.
All right, let's take a look at this. The limit as x approaches infinity of natural log of x over 2 root x. What should we do first?
Plug in 0.
All right, so if I plug in infinity, what's the natural log of infinity? What happens to natural log as x gets very large?
It gets very large.
It gets very large. And what about 2 root x as x gets very large? That square root also gets very large, right? Neither of them get large super quickly, but they both increase forever, don't they? Without bounds, there's no asymptote on them going to the right.
Yeah.
Yeah. So we should be able to then use L'Hopital's rule to give us the limit as x approaches infinity. What's the derivative of natural log of x?
One over x.
And the derivative of 2 root x ought to be 2 times the derivative of root x, which is 1 over 2 root x. So really just 1 over root x there. Can I simplify 1 over x over 1 over root x? That'd be root x over x, right? Which would be the limit as x approaches infinity of, it's x to the 1/2 over x to the first. That would just be x to the 1/2 in the bottom. And if I plug in infinity to that, I have 1 over a very large number, which is
Which is 0.
Which is 0. Great. Everybody good with that? Or no?
Yeah.
Okay. We might want to note something about this function, and that's that the square root function increases more quickly than the logarithmic function. What's the slowest increasing function are logarithmic functions, right? And then what's faster than that? Root functions are faster than that. And then what's the next fastest after, cube root, square root functions? something like a polynomial function, right? Degree of 1, right? A linear function will increase more quickly than a square root function, but a parabola will increase more quickly than a first degree, and a cubic will increase more quickly than a parabola, and a 4th degree will increase more quickly than a 3rd degree, and a 100th degree polynomial will increase more quickly than a 99th degree polynomial. And then what's faster than a polynomial function?
Exponential.
Exponential function. So as x goes towards infinity, e to the x increases more quickly than x to the 100th power. In fact, very, very much more quickly, right? I mean, it's crazy how much faster exponentials grow than polynomial functions grow. E to the x or 10 to the x, the higher the base, the slightly more quicker it's going to grow. Anybody know the function that increases more quickly than an exponential function? Nobody? You don't need to worry about these, but
Is it like e raised to e to the x?
no, that's still a different type of exponential. It is a factorial function. You familiar with factorial?
The upside down exclamation point.
It's actually a right side up exclamation point, but this isn't Spanish where you turn the exclamation point upside down at the beginning. Math is a universal language. It's not one specific language. Oh man, that was deep. Not really. Right? 5 factorial means 5 times 4 times 3 times 2 times 1. Or 100 factorial, 100 times 99 times 98, and so on. This will increase more quickly than exponential, but you don't need to worry about this. So if the thing in the denominator grows more quickly than the thing in the numerator, right, a root grows more quickly than a logarithmic, it should tend towards 0. But if I had something in the numerator, if we're going towards infinity, something in the numerator that grows more quickly than the thing in the denominator, then this should go towards infinity because the top is growing more quickly than the bottom. But if I flip it around so that the bottom is growing more quickly than the top, then this number is always bigger than this number as we go towards infinity, which means it's tending towards 0. Good or no?
Good.
All right. Wonderful. Let's, just for fun, what if I gave you this? The limit as x approaches infinity of, how about x to the 5th power over the cube root of x. What should that be? Without using L'Hopital's rule, just by using that list of how quickly things increase and decrease.
Infinity.
It should be infinity, right? The numerator is growing more quickly than the denominator. What if I gave you this one? The limit as x approaches infinity of, let's say, the 8th root of x over natural log of x.
Infinity.
Should be infinity, right? The root grows faster than the logarithm. I give you the limit as x approaches infinity of x to the 1000th power over 2 to the x. What should that be?
0.
Should be 0, because the denominator is going to increase more quickly than the numerator. Good or no?
Good.
Everybody feel all right with L'Hopital's rule and also this sort of just ordering of how quickly things grow. That's it for today. So L'Hopital's rule works for 0 over 0, infinity over infinity. Just take the derivative, do it as many times as you need, as long as you keep getting an indeterminate result. And then these little orders of how quickly things grow. If the top grows more quickly than the bottom, infinity. And if the bottom grows more quickly than the top, 0. Only as we go towards infinity. And that's going to be it on our new material for today, and it on our derivatives, our applications of the derivative. That's all. They're finished. Hooray. Number 6 from the homework. Here is one 6-foot pole. Here is one 8-foot pole, right? 6 feet and 8 feet. And then we've got a rope or a chain or a cable or something that's going down, touching the ground in between them, starting at the top of the 6-foot one, touching the ground, and going back up and touching the top of the 8-foot pole. Yeah? That sound about right? And I believe we were given, these are vertical or whatever. And then the distance between was how much? 10 feet?
Correct.
All right. Okay, so this is our basic setup, and it asks us what is the minimum length of cable that we could stretch between these 2 points by having it hit the ground somewhere in between. Doesn't matter where in between we hit the ground, we just got to hit the ground somewhere in between. So let's call this A, and let's call this B. This length A plus B, right, is what we want to minimize, right? We want the length of A plus B to be as small as it can be. Everybody good with that?
Yes.
All right, so then we need to find an expression to represent A and an expression to represent B, add them together, and minimize. Okay. So let's go ahead and see if we can write an expression for that. Do we know how far away from the first pole we're hitting the ground? That's what we're looking for, right? We know that it's somewhere between, 0 and 10 feet, but we don't have a specific value. So let's just call that our variable, because that's what we want to know, is how far away from the first pole should we hit the ground. So if that distance is x, then this distance here ought to be 10 minus x. Yeah?
Yep.
Okay. And so now I should be able to say that a squared is the square root of x squared plus 36, right? Using the Pythagorean theorem, x squared plus 36 equals a squared. A squared is root x squared plus 36, or not a squared, did I say? Ah, geez. That should just be a equals the square root of that. There we go. Good with that? A is the square root of x squared plus 36. And b should be the square root of 64 plus 10 minus x squared. So what does a plus b, what is the total length of a plus b equal? It equals the square root of x squared plus 36 plus the square root of all of this, which is x squared minus 20x plus 100 plus another 64. Good or no?
Good.
Who was it that asked this? Now I forgot. Okay, you got this far. Yeah, all right. So now we need to minimize L. So we're going to take the derivative of this function. So L prime ought to be, which should be 1 over 2 root x squared plus 36 times the derivative of x squared plus 36, which ought to be what?
2x.
Which is 2x. and then plus 1 over 2 square roots of this, x squared minus 20x plus 164 times the derivative of that, which ought to be
2x minus 20.
2x minus 20. Good. All right, so now we'll do just a bit of simplification before we try to figure out when this equals 0 and when this is undefined. So first off, I can cancel those 2's. And then this one, I can take a 2 out of this, right? Make this 2 times x minus 10. And then I can cancel those 2's. So I think that'll make life a little bit easier. And I'm going to go on to the next page here and say we've got L prime is equal to, so now we've just got x over root x squared plus 36. Plus x minus 10 over, what was it, x squared plus, or no, x squared minus 20x plus 164. And if it were me, I would just go in and use a calculator to figure out when that's equal to 0. So I'm going to open up Desmos. And if it turns out, I don't remember offhand if this comes out to be a nice, easy number. If it comes out to be a nice, easy number, we'll go through and do the arithmetic to show that. Okay. X over root x squared plus 36 plus, what was the other one, x minus 10 over root x squared minus 20x plus 164. And it looks like that crosses through at 4.286, which doesn't seem like a real nice, easy value, so we'll just use that value. Just looking at the graph of this, we could probably see that it's not ever undefined, right? At least definitely not anywhere between 0 and 10, which is what x would need to be. So the only place where we could have a minimum is at x equals 4.286. So we'll say this equals 0 if x is about 4.286. And using our sign chart, just real quickly, the derivative goes from negative to positive. And if the derivative goes from negative to positive, that means that our function goes from decreasing to increasing, and it means that we have a minimum there. Is that good for everybody? Yeah, so the best way to figure out when that equals 0. Sometimes these like messy ones will algebraically work out okay. Looks like this one did not. So comes out to be, much easier to do it using the graph to see when it crosses through. Does that help, Rhea? Great. Anybody else have any other questions on that or any of the other ones?
Could you go back to the first slide for a sec?
Sure. There you go.
All right, thanks.
Yep.
And just to clarify, the sign chart is just to confirm that that x produces a minimum.
Correct, that it's a minimum rather than a maximum. Yep.
Okay.
And yeah, normally we plug it into our actual derivative, something bigger and smaller, but since we happened to have the graph, we can just look and say, well, to the left of that it was negative, and to the right of that it was positive. So, and this is the graph of the derivative, which tells us the function itself goes from decreasing to increasing. Any other questions on any of the options? Sorry, go ahead.
Would that be your answer?
Yeah, so we'd say x is 4.286, what was it, feet or meters, or I don't know what it was. Feet. So feet from, and x was the distance away from the 6-foot pole. So we'd say 4.286 feet from the 6-foot pole. And you may have set yours up differently if you were working on this one on your own. You may have set yours up so that this distance was x with the 8. So you might have had x squared plus 64, and then you might have had 10 minus x squared plus 36. And you would have still got, when you found the critical value of that, you just would have got 10 minus 4.286 as your critical value. And you would have said you're that far away from the 8-foot pole.
So we don't have to like plug it back in and find the length of the cable.
I don't know. Maybe did the problem say to do that?
I think so. That's not that hard though.
Yeah, I mean, if it said to do that, then yeah, just plug that number into the original length equation. But if it doesn't, then this is good enough. Any other questions?